Shouldn't clap when I'm holding the mic. So today's colloquium we'll have Adam Frank, who is a professor at the University of Rochester. He got his PhD at the University of Washington in Seattle, which is where I know him from, and did a Hubble Fellowship at the University of Minnesota. Adam is a theorist whose large-scale numerical simulations address the magnetohydrodynamic evolution of matter ejected from stars. That includes jets from young stellar objects, bipolar outflows from AGB stars, mass transfer, and orbital evolution in AGB binary systems, which you may have heard him speak about earlier today at lunch. Adam's group at University of Rochester developed the AstroBear adaptive mesh refinement code used for simulating magnetofluid dynamical flows to study those kinds of processes. You should definitely check out the AstroBear YouTube channel, which has some very nice simulations. And speaking of bears, Adam loves to study nature through mathematics, computer simulations, and hiking in the woods. Indeed, he and I have backpacked and skied quite a number of miles together, including sledding on hefty bags in the Cascade Mountains.
In June.
In June. In the public arena, Adam is the co-founder of NPR's 13.7 Cosmos and Culture blog, which you should also check out. He's a regular contributor to NPR's All Things Considered. He's got more than 3 or 4 dozen articles in Discover and Astronomy magazine, and maybe a dozen op-eds in the New York Times by now. He's also a book author. He wrote The Constant Fire, Moving Beyond the Science and Religion Debate. He wrote About Time, Cosmology and Culture in the Twilight of the Big Bang. He wrote a textbook recently called Astronomy at Play in the Cosmos, which is very nice. And his newest book is called Light of the Stars, Alien Worlds and the Fate of the Earth. So today Adam is going to talk about how our industrial civilization is like a cosmic teenager, just beginning to realize that they're holding the wheel and finding out that it's time to drive and maybe avoid that steep cliff, which reminded me of James Dean in Rebel Without a Cause, which you'll note took place right next to the Griffith Observatory. So there's a tie-in there. So what's happened to other civilizations under similar circumstances to ours? Admittedly, constraints on the statistics of civilizations in the universe are right now pretty meager. But we could have said the same thing about exoplanet statistics just a couple of decades ago. So now's an excellent time to consider these kinds of cosmic questions. Unfortunately, my introductions left no time for Adam.
You can give the talk. Thank you, Paul. It is a great pleasure and honor to have a chance to speak before you guys today. So, yeah, the topic here is what I call the astrobiology of the Anthropocene, which is a project I've been working on for the last few years. You know, the elevator pitch is climate change for aliens, right? And so, you know, we're going to talk today about why it's reasonable to talk about aliens in this question of what's happening with us right now. So I just need to let you know that thinking about aliens is not my day job. My day job is doing things like looking at exoplanet evaporation. And here's a simulation from my group where we're studying. This is a star here, and this is the rotating frame. There's a hot Jupiter, and the hot Jupiter is expelling a wind which remarkably doesn't just blow away. It actually goes into orbit around the star. So this is what I do. I think about during the day with my research group. But I also have a night job, and that is doing science writing. And I've been doing this for a long, long time. Like many people, I was deeply inspired by Carl Sagan. And in particular, I've been taking on issues surrounding climate change and science denialism. I mean, I write about a lot of other stuff, but this has been consistently something I've worked on. So here's a post or an op-ed I did in the New York Times a while back. And whenever I do something like this, literally there's 300 hate mail emails coming within 20 minutes of its. So the thing is, and this is when I did right after Trump came in, or Trump was going to come in, the idea of cutting NASA. This was before the Republicans won, and how they wanted to cut NASA and why that was a bad idea. But the point is I've had a lot of time and a lot more experience than I probably wanted in dealing with climate denialists and trying to understand why are people against this? Why the data for climate change is so overwhelming? Why are we still having this debate? So the interesting thing is this project I'm going to tell you about came as an intersection of my day job as an astronomer and my night job as a science communicator. That's really where this project came from. So it was sort of, as I was writing for things like NPR, what they call the Cities Project, I did a bunch of work for them, thinking about, trying to communicate thinking about cities from sort of, the planetary view, that I started down this road about thinking about humanity and its impact on the planet in a general way, right? And what do we mean when we talk about, what is the thing we're really pointing to when we talk about humanity's impact on the planet? It's what's called the Anthropocene, right? And so this came from a paper by Crutzen and Stomer in 2002, where they suggested that human activity, they looked at the data, but they, suggested that human activity is now the fundamental driver of the coupled Earth systems. And because of that, millions of years in the future, there will be a layer, a strata, which will show this transition that we're going through. So there's been a lot of debate about whether or not, we need to name this stratigraphy, I can't pronounce it, whether this is going to show up on the strata. But this idea that human activity is now the fundamental driver of coupled Earth systems has, there's lots and lots of evidence for this. So the whole idea behind the Anthropocene, when you go back and sort of, look at it from a longer view, it's all about the coevolution of the coupled planetary systems. What does that mean? What did we talk about when we're talking about the coupled planetary systems? It's that basically we have the atmosphere, the hydrosphere, which is all the water, the cryosphere, the ice, the geosphere, or sometimes people will call this the lithosphere, and the biosphere. And that these are all, strongly coupled. And the evolution of the Earth, I love this little cartoon, the evolution of the Earth from the Archean all the way up to the Holocene, where now the last 10,000 years we've been in the Holocene, has been a history of the coevolution, of the, arrows going back and forth between the evolution of life and the evolution of the planet. And that is really the idea that, we want to think about when we're thinking about the Anthropocene in a general sense. So coevolution, I really am emphasizing this idea of coevolution. The Earth system scientists have now, this is, an important idea for them. And it's basically that, life and the Earth, the coupled systems I just talked about, have been evolving together. You can't separate them out for a long time. So here is a paper figure from Schnellenbacher, I think this is like early 2000s. But it's on this side is the evolution of the Earth environment, important events, and here are important events in the history of the Earth. And for example, once oxygenic photosynthesis was invented by life, it led to the Great Oxidation Event, which completely changed the evolution of the planet, right? In so many different ways that it's hard to enumerate them all. But certainly things like the ozone layer, et cetera. And that this has been going back and forth. You can't separate the biosphere. Life is not some scruff sitting on top of the planet that doesn't have much an effect. Perhaps in the Archean early on, it was a bit thinner, and we'll talk about that later. But once you get certainly to the Great Oxidation Event, life is a full-scale player in the evolution of the planet. Okay, so the Anthropocene, the idea of the Anthropocene is that that we're having this very strong effect on these coupled Earth systems, and that in particular, if we want to have a sustainable version of our civilization, we need to be mindful of these interactions. And in particularly in this paper by Rockstrom and then another paper by Stefan et al., they were all together on this. There were two important papers where they proposed these idea of planetary boundaries, that you could identify different parts of the coupled Earth systems, and you could identify the impact we've been having. So, for example, climate change. If you look at the CO2 concentration, pre-industrial value is 280. Current value is 380. It's beyond this now, right? 387. And the boundary they proposed was like, look, don't go past 350, or bad things are going to happen. Biodiversity loss, the nitrogen cycle, the phosphorus cycle. These ones, particularly the the nitrogen cycle, you can already see like pre-industrial value of moving nitrogen around was 0. Now it's 121. They suggest 35. So I love this diagram. This is the Earth, and these are all the different boundary categories, and then how far up you are on this line tells you how close you are to the proposed boundary. So genetic diversity, we've already pushed past the boundary. Nitrogen, we've already pushed past the boundary. Climate change, we're heading there. This is this very detailed idea about thinking about the coupled planetary systems and the impact of our industrial civilization with the goal of figuring out what is sustainability. The only reason why you want to have these boundaries is you want a long-term version of our civilization. But that leads to what I'm going to call the astrobiological question. What I'm going to propose today is that it's going to be very fruitful to ask these questions in an astrobiological context. And I'm going to do this in a bunch of different ways. And the first way I'm going to do it is, we're all interested in creating a sustainable version of our civilization, but how do we know that's even possible? How do we know that such a thing exists? In other words, in the cosmic inventory of things that the universe has made, comets, black holes, fill in your favorite thing here, how do we know there's such a thing as a sustainable, long-term, energy-intensive civilization, right? We don't know that that's a thing. And actually, just by asking this question, we sort of change the framework that we're thinking about the Anthropocene in. And so what I'm going to propose today and go through is the beginnings of sort of figuring out how to look at the Anthropocene from an astrobiological perspective, and even what kind of science can you do about that. So the goal is to develop an astrobiological perspective on what's happening to us now. That will carry two scientific premises with it. The first one is that the ongoing astrobiological studies of the coupled relationship between life, planets, and their coevolution can inform new perspectives on trajectories into and through the Anthropocene. So, this is not wildly provocative. It's just saying, like, look, we've already learned, we have a bunch of planets that we've studied climate on now: Mars, Venus, Earth, Titan. We have the entire 4 billion year history of the Earth well mapped out. These, if we bring these to bear, we might be able to learn more about what does it look like to head into an Anthropocene, and what does a good Anthropocene look like, right? There's no way to avoid the Anthropocene now. The question is, can we mitigate the effects on the changed planet? But I want to go beyond that, because the astrobiological perspective takes you beyond that. And that at least the second premise, is that Anthropocenes can be seen as a potentially generic planetary transition. In other words, we're not the first time that a civilization has triggered an Anthropocene. Okay? So the specific questions I think that you can address scientifically, that you can do something with, even right now, if most of it's going to be theoretical, there are a few questions we can ask, and that's what the rest of this talk is going to be about. So first of all, how common are Anthropocenes? On a given planet that generates a civilization, does it matter where your planet is in terms of its orbital location, where it is in the habitable zone? Does it matter about the atmospheric composition? Is almost everybody going to trigger an Anthropocene, or is it very rare? Next, how fatal are Anthropocenes? And this question goes right to the Drake equation, because what is the average lifetime L for industrial civilizations? At least up to the point where we're at now, right? If we progress 100 million years into the future, who knows what existential threats there'll be. But just, how long can you get when you're in the phase where you're having a strong effect on your planet? And then finally, what properties characterize planets with long-term industrial civilizations? Can we think biospherically and ask ourselves, if you manage to get into a sustainable setup with your planet, is there something generic about those properties of the planets? And we're going to think about this from a thermodynamic perspective. Okay? All right, so but there's a principal requirement in doing this, right? In order to do this, in order to have the astrobiological perspective on the Anthropocene, you have to take exo-civilizations seriously. And right there, I'm already making a change. I don't want to talk about aliens. I want to talk about exo-civilizations, because God knows we're talking about exoplanets, and we're talking about exobiospheres, and we're talking about exobiology. So the idea that somehow this we're never allowed to talk about, is just a holdover from another era. But for what I'm going to do, I'm not particularly interested in detection. So some of stuff, what I'm talking about, may be useful. Techno-signatures is something absolutely we should be thinking about. We're going to be staring at all these planets via the transiting for the next 50 years. The idea that we'll never talk about the possibility of that something that we'll find will have something to do with technology is a little strange. But I'm not interested in it right now. I'm certainly not going to talk about biology, about exo-civilizations. I don't think there's a lot of constraints to say what an intelligent civilization is going to be like in terms of their biology. And I certainly don't think there's any constraints for sociology, right? Interstellar economics, you can do it. It's fun if you want to do it, but it's basically a science fiction story. I'm really interested in places where there are some constraints, where there's something you can do, something we've learned to at least look at the contours of the questions and the solutions. So what I'm going to focus on is coevolution. I'm interested in the coevolution of the civilization and coupled planetary systems. And I'm going to argue that there are, in fact, actually rules that we can use to say something about this. Okay? And I also want to point out, so why do we have this bias against thinking about exo-civilizations? And the answer is prosthetic foreheads. Right? So as Jason Wright talks about, the giggle factor when it comes to aliens. We've been inundated for, decades with bad TV science fiction where, all the aliens that just have prosthetic foreheads. And it's made it difficult to talk about it without the giggle factor. And then, of course, you got UFOs and such. But I think, what I'm going to argue is that, there are some places where you can do some science related to exo-civilizations. And remarkably, the one place where I think you can do that science is directly related, or at least can relate, to the question of what's going on with us in the Anthropocene. So it can actually give us a perspective that may be very useful as we're trying to navigate the Anthropocene. So now I want to move towards, moving towards a science of exo-civilizations. This is the project that I've been working on with some collaborators. So these are basically theoretical studies of exo-civilizations that will be relevant to Anthropocenes. Okay? So the first question, of course, if you're going to think about, you want to know what is the average lifetime of a civilization, and what do you want to know what is, on average, how fatal are Anthropocenes, you need a statistical ensemble. Is it reasonable to think about a statistical ensemble of exo-civilizations? And of course, this leads us right to the Drake equation, which you guys are all very familiar with. So the book that I did, it was great to go back to the history, to look at the history of what Frank Drake did and what was going on in that meeting. That was really fun and fascinating. But you guys are all familiar with the Drake equation, where basically this is n is the number of civilizations that we could get signals from. It's about what's happening now so that we can get signals, right? And then there's these three terms, the star formation rate, the fraction of planets, and the number of planets in the habitable zone. These all have to do with astronomy. Then there's the fraction of planets that formed life, the fraction of that life that goes on to intelligence, and the fraction that developed technology. These are all about, biology, sociology, and evolution. And then there's this term, the sort of term that looms over our heads, which is how long in general does a civilization last? So in 2016, Woody Sullivan and I were talking about this, and our idea was that, look, you got all this Kepler data, right? So, what's happened essentially is that the Kepler data has nailed these two terms, right? In the beginning, this was the only term we knew, but now we know all of the astronomy terms. That ought to be useful for something, saying something about exo-civilizations. The question was, what could you say about it? So that's why we came up with this idea of the archaeology of exo-civilizations, because what we meant is we're going to drop the L factor. We're not interested in whether or not they're around now. We just want to ask the question, we want to formulate the Drake equation in a way, we'll call it the A form, where we're just interested in how many civilizations have there ever been. Right? How many civilizations, I don't care whether they lasted 10 years or 1,000,000 years, how many have there ever been? So if I drop the L term and I write the Drake equation as all the terms having to do with astronomy and all the terms having to do, with life, then, I can write it this way, where I have A equals N astro and F. We'll call this the biotechnical probability. This is the probability to run all the way from forming life to getting a civilization. It's the whole enchilada. So what you can do now is if you set A equal to 1, you can use the Kepler data to get a limit on an empirical limit on the biotechnical probability. And it's basically just, you set A equal to 1, and it's 1 over the basically the number of habitable zone planets in the visible universe. And that turns out to be 10 to the minus 22, approximately 1 in 10 billion trillion. How do you interpret this? This is basically if the only way that we are the only time in cosmic history that there's been a civilization is if the nature's choice for the probability per habitable zone planet of forming a technical civilization is less than 1 in 10 billion trillion, right? So we don't know what nature sets on this, but we call it the pessimism line, right? Because the whole problem with the debate over life in the universe and intelligent life, it's been a battle between pessimists and optimists, right? And the optimists say, oh, all those terms are 1, right? And the pessimists, well, how low is pessimism? How low do you have to go to be a pessimist? And in that way, it's really useful to look at the history of this debate. So many of you know Ernst Mayr, the biologist. He was a famous pessimist. And if you go through his work, you can get a value of what he thinks probability per habitable zone planet is, and he has 10 to the minus 15. He thought intelligent life was going to be very, very rare. But his value, there's 7 orders of magnitude larger than the pessimism line. Likewise, Brandon Carter, who did this ingenious argument for calculating the biotechnical probability, gets 10 to the minus 20, and he writes, this value is more than sufficient to ensure that our stage of development is unique in the visible universe. No, there's still 100 times that it's happened, right? We're not going to see them, we're not going to get evidence of them, but if we're thinking theoretically, does it make sense to think about a statistical ensemble of trajectories of civilizations, then, even Brandon Carter turns out to be something of an optimist, right? So that's why I kind of think of the pessimism line, it's something like a Planck length for astrobiology. It sets for you simple numbers, and it sets a line between, if you want to go out and you calculate this biotechnical probability. If it's less than this, yeah, we're the only time it's ever happened, right? But if it's more than this, we're not the first time to experience what we're experiencing in terms of developing a civilization, okay? So, for example, if nature chooses 10 to the minus 13, which would certainly give us a sterile galaxy, you'd still have 1 billion civilizations that have lived. So that's 1 billion trajectories in my phase space that I want to create of exo-civilization trajectories. So now let's think about, okay, so I now have argued, at least to myself, that it's okay to think about, a statistical ensemble of exo-civilizations and their histories. How can I actually model what those histories might be? So we can turn to dynamical systems theory, right? And these are the original paper that Woody and Sullivan and I did the first time was 2014, and I'm also going to show you this new work, where we're going to try and use dynamical systems theory to try and model the interaction between a civilization and its coupled planetary systems. And the model here is the famous predator-prey model, where you've got an equation for the prey, which are the bunnies, and the equation for the wolves. And they're coupled by their, the birth rates and death rates and capture rates, etc. And what you find is, this beautiful behavior, which you wouldn't know about unless you solved the equation, though it's seen in nature, is that, predators and preys, both populations oscillate but out of phase with each other. So this is the dynamical system theory for population biology. And I'm going to argue that population biology is actually a good place to try and start doing this. So what we want to say is, look, we're interested in exo-civilization evolution. Obviously, it's going to be a very complicated problem, but can we think of a reduced parameter space or phase space to do this problem in? And yes, I think we can. First of all, the first parameter you're interested in is the population, right, where n equals 0 means you're extinct. Then the energy per capita, right? The energy per individual in the species, right? So when human beings started, we all had 1 human being's power per human being, right? When we were hunter-gatherers or before even that. But now the average American household just from your house gives you 50 human beings worth of power, right? Every time you plug in, you've got basically 50 servants available to you. And, a lot of those, that doesn't even count your car. So, this is a measure of how good you're getting at harvesting energy to do things. And then there's your feedback on your planet. So you could do something like the ratio of the forcing on your planetary systems due to the technological activity divided by the natural forcings, whatever is just coming out, the way in which just plate tectonics or et cetera is changing things. So these 3 are a good way of thinking about the evolution of exo-civilizations and their planets. And so you'd have some model. The dynamical equations would be, differential equations for these. The right-hand sides here would be models that you'd come up with, hopefully using climate, what you understand about climate, basic ideas from population biology. And then you'd look at the evolution in this phase space to tell you about the history of the civilization. So what we might hope, this is what Woody and I did in 2014, is that you'd see things like, trajectories that were clearly collapse. You start off with a low population, right? A young civilization. You start climbing the curve of technology, so you can harvest more and more energy. So you're getting, more per capita energy consumption. But as you do that, you start turning in this direction. You're forcing the planet more, and the impact of the planet changing the state from where you were born in leads to some kind of instability, and boom, you die, right? So that would be a collapse trajectory. And then you could imagine a sustainable trajectory, which starts off the same way, but somehow the civilization figures out what it's doing, and you end up with some nice, stable fixed point or limit cycle where you have lots of energy per capita, so you're not, you haven't gone back to caveman age, but you don't have so much planetary forcing. So you basically come into a sustainable long-term state. Okay? So it's interesting to look at this phase space diagram for us. So this is, green is world energy consumption. So that's the proxy for per capita. Global population is yellow, and red is CO2 concentration, which is your forcing on the planet. And so if we put that into that phase space, here's what we see, right? Kind of exactly what we were thinking. We're a young civilization. We are driving very quickly up in population and in per capita energy or total energy, but we're also moving, deep into the phase space where the forcing is occurring. So what's going to happen now up here, right? Do we come down? Do we find sustainability? But we want to ask this generally, right? I'm interested in asking this in a general way. So, what we want to do is start modeling this, right? So I've given an outline of how you could do it. So in this recent paper that's coming out in 2018, we actually did some, very simplified models to get started with. And I want to point out in particular, Jonathan Carroll-Nellenback. He and I developed these equations, but he's the one who did all the beautiful dynamical systems analysis. And if you're going to ask detailed questions, we're going to have to go back to the paper in some case if you want to ask about the Jacobians and such that we had to take to find out the fixed points, etc. But okay, here's our model. We have an equation for the population. We have an equation, we'll call this it's the environment. Think of it as the temperature of the planet, right? And we have a term, this is what's called the logistic equation. This basically gives you the natural birth and death rate of the population, where this term K is the carrying capacity, right? It tells you how much of that species you can have. But we're going to add to this also a term that has to do with when you use the planet's resources, you get a birth benefit out of this. You get more individuals because you're using the planet's resources. Likewise, the environment or temperature, its state, we've got a term here which will, if you push the planet, it'll naturally come back, right? But we also have a term here that the more you use the resource, the more the population is using the resources, the more you're increasing or heating the environment. So very simple model, but most importantly is you see that the carrying capacity depends on the state of the environment. So as the environment gets further and further from where you started, the carrying capacity comes down. So it drives your, so this is sort of the way, this term tells you how the population is affecting the environment. This term tells you how the environment is affecting the population. Okay. I won't go through this in detail. You can just non-dimensionalize these things. You get a lot of non-dimensional parameters, which actually, if we wanted to go really into, we could talk about the meaning of those, but we don't need to. So here's our first model where we had a civilization and a planetary system interaction, and we just imagined there was a single resource with some impact. And so you get these beautiful plots, phase space diagrams, where you have to find the nullclines of the two variables, and where they intersect is an equilibrium point, and then you have to take the Jacobian of the equilibrium point to find whether it's stable, unstable, etc. And there's a whole classification scheme of, you can have you can even get limit cycles if you go through a Hopf bifurcation. But the important point to see here is, so this green line is actually a given trajectory. We start off with some values, with the population very low and the environment pretty much where, the civilization started. And you can see you climb around here and land on the equilibrium point, which is stable. So what does that actually look like in terms of the population and the heating? So you get a lot of, based on this parameter delta, which is really a measure of the environment's sensitivity to your growth, you get, these solid lines are the population. And you see the population grows very quickly. And then for some cases, it drops. It dies off. You get a die-off. So this class of trajectory we're going to call die-off. These dashed lines are the environment, and you just see the environment growing heating up. But, for all these models, you'll eventually reach a steady state. The question is, how'd you reach it, though? So there's, there's values of these parameters where you can get 90% of your population dying off. And for a complex technological system, which is a bunch of networked, coupled networks, it's not at all clear that you could survive losing 9 out of 10 members of your society. Okay, and there's also, good news, there's also smooth landing. There's solutions where you basically increase up to a certain point and you reach that fixed point without losing a huge amount of your population. So you come to a steady population. So that's good news. Now we did actually a whole bunch of models, but let me point at this next class of models. This one was, now we wanted to include the possibility that the civilization saw what was happening and could switch from a high impact resource to a low impact resource. So that is actually here. This is a heaviside function, or almost a heaviside function. And these parameters basically say, these are just parameters. So we don't have any sociology except for parameters. And the parameters are, at what temperature in the environment does the civilization recognize, oh my God, we're doing something, let's switch from the high impact to the low impact resource. Okay, so that was a change in the equations for the planetary state, the temperature. And we also added this term, which is a nonlinear interaction term, or a nonlinear feedback term about internal dynamics, right? We know with the Earth that it's a complex system. There are attractor basins. If you push the Earth systems too hard, it'll roll down from the state that you're in into another state. So there's internal dynamics. So, even if we keep the CO2 level at, maybe only to 420, we don't know whether or not we're going to trigger internal dynamics, which will carry the Earth onto another state. And this term here is a measure of that, or this term is going to drive that. So these models, they're not that much more complicated, but they have more going on in them. And so if you look at the phase space diagram for this, so this is the case I'm going to show you where there's only, I'm not going to include 2 resources, I'm only going to include 1 because it makes the phase diagram easier. But now, rather than 2 straight lines, this is the same null cline we saw for population, but now the null cline for the environment is now a parabola, right, because of that nonlinear term. And that means you now have 2 equilibria. Well, you also have, this term is an equilibria as well. And the phase portrait is much more complex. These equilibria can be stable or unstable depending on the parameters that you use. So it's a very, very beautiful and very rich set of behaviors that come out of this now. We haven't added much. We just added, a nonlinear term, some internal nonlinear dynamics. So what do you get out of that? So the interesting thing is, so in all of these plots, these are the plots for green is the population, red is the temperature, right, the planetary state, and these are for a bunch of different parameter regimes. And what we see is, once again, let me put this, we have the die-off solutions, right, where the population, starts to multiply very quickly, the planet heats up because of it, you overshoot your carrying capacity, and you end up, coming down, you have to lose some fraction of your population and come down to a steady state. We also have our soft landing or sustainable solutions, right, where just smoothly you reach your steady state. There's no pain and suffering. But there's also what appears now are true collapse civilizations, true solutions where the temperature runs away and your population just dives down. So, that's the bad news about these solutions. There's also, like I said, it's quite rich. You can also get limit cycles. That's really interesting, where the population is oscillating. And you can do the analysis to look whether that's a Hopf bifurcation or not. But so, it was nice to see, because this was the idea. These were simple models, but we wanted to see what classes of behavior was hiding in these simple models. Because as we go to more complex models, that's what we're looking for. We're looking for classes of behavior that will tell us about how long do Anthropocenes last, or how easy is it to trigger Anthropocenes, how long do they last, what does the civilization have to do, what choices does it have to make to survive. I'll note that once we added resource change, where you went from fossil fuels to solar or something, you could still be surprised because of the nonlinear term. So here is the growth of let's look at the growth of the temperature. Temperature increases as the population increases, and then you make the change right around here, and it looks like, oh, things are leveling off, everything's great, but the nonlinear runaway term catches you, and you get swept up to high values of the temperature, and the population still collapses. So, I'm not going to read too much into these models, but it was sobering, right, to see that even if you make the change, these models have this possibility that it's too late, that you're not going to survive. Okay? All right, so that's the path forward, or one path forward. So what are the next steps with this, right? So the model I showed you was very simplified. It was fun to, look at. But what we're going to want to do is make the models more planetary physics specific. In particular, we're going to want to include planetary parameters, right? So things like the orbital distance. How far does it matter where you are in the habitable zone? So like talking with people like Jim Casting, who, has done a lot of the work on habitability, he thinks that no matter where you are in the, unless you're in some very special locations in the habitable zone, that it's going to be very hard for you to not trigger climate, some kind of Anthropocene, some kind of climate change by dumping lots of by using lots of energy. Stellar type, right? How does it matter about your radiation that's coming from the planet? There's how close you are, and then of course atmospheric constituents. Did you start off with an atmosphere that was are you CO2 breathers, or do you have less oxygen than we have? Okay. So as an example of at least heading in this direction, this is from the Way et al., where they used a full climate model, a full generalized circulation model to model Proxima Centauri b, as well as, and compare it to the Neoproterozoic Earth during the snowball phase, right? So the question would be eventually, right, I still think we're going to work with pretty simple models to begin with, but eventually you're going to want to use full global climate models and put in the impact of a technological civilization, just like people are doing models of these things by putting in biospheres to see what the impact is. So that's eventually where you would head with this. Now, I also want to point out one of the things you need to do is also put in explicit resource couplings. So in the model I showed you, the resource was just some very generic thing. Some had high impact. We had either had high impact or low impact. What does that mean? Well, what we know is that a young technological civilization is only going to have so many energy modalities available to it, right? So, certainly if there's biomatter, there's going to be stuff to burn. Now, whether or not you got fossil fuels or not is an interesting question. I've posed this to a bunch of Earth scientists, and I thought like, fossil fuels, it's going to be really hard to get fossil fuels. But they, most of the people I talked to, not that it means anything, but they were like, oh yeah, it should be pretty easy. The conditions, should be available. So I don't know, but you've got combustion. Clearly wind is going to be available, geothermal, tidal, nuclear. But what I'm going to argue is this is a pretty exhaustive list. You might want to come up with a weird thing where you got like, super strong magnetic fields, but for a young civilization, right? And this is the idea of having, we're going to do this work where we have gutters, gutter rails when we're bowling, right? That, we're not going to imagine the civilization has Z-rays or some kind of, science fiction technology because we're not going that far into the future. We're really interested in what's happening to us, what happens to young civilizations. And I believe you can argue that this is it. This is the only set. You're only going to get what the planet gives you. Oh, did I not have solar on there? Oh my God, yeah, there should be solar. Thank you. Yeah, solar, right, is hugely important. Oops, that's a big one to miss. And most important, we can calculate the feedback from these, right? So, in 1903, Arrhenius did the calculation for the feedback, the planetary feedback from burning fossil fuels. This paper is very interesting because this was Miller et al. In 2012, and they asked the question, if you tried to power this civilization by extracting wind, only wind, what would be the impact on the planet? First of all, how much could you actually extract, and what would be the impact on the planet? It was a very interesting study, and particularly what they did is they ran global climate models, and you find that if you're using that much, if you're extracting that much energy out of the kinetic energy system of wind in the planet, that you still end up with something akin to, it acts like 2 degrees of warming, right? So 2 degrees is not so bad. If you stay at 2 degrees, we all kind of agree that 2 degrees is where we should be staying. But there's no free lunch. I mean, that's an important lesson of thinking about the astrobiology of the Anthropocene as well. It changes how we think about where we're going. There's no magic bullet. If you want to have a world-girdling technological civilization, you're going to change the planet. You're going to have some kind of effect on the planet. Okay, and so, where does this all lead? For me, one of the most important places is that you're going to be able to get a theoretical estimate for Drake's final term, right? So how does that happen? So, I have all these variables, associated with the planet, associated with the energy sources civilization uses. So I'll perform a large-scale simulation campaign, sampling the initial condition space both for the planets and the civilization. I'll run 1 million models. And then out of that, I expect I'm going to get bundles of trajectories in my phase space, right? And I can analyze the properties of these bundles. And there's many things I could learn from that, but one of the results I'll just get is the average lifetime of a species, okay? And so why is that important to us? If I do this theoretical calculation and I find that the average lifetime is 200 years in my model, that implies we're in trouble, right? It means that you're trying to search, you're trying to get through a narrow window that, in your choices, and you may not have a lot of room for error. Whereas if it comes out to be a million years, then we have a lot of wiggle room. We can make mistakes and probably still make it through. So, to me, this is something that would be useful, right? This would be something that would tell you something, where these models would at least lead you to some different way of thinking about what's happening to us now. Okay, so I now want to switch. I'm not going to talk too much about this, but one of the other things we asked, the question, or the other questions I posed was, okay, if you do make it to sustainability, what, on average, what are the planetary characteristics of a planet, a biosphere that has a technological civilization that has reached a long-term sustainable version of itself? Okay. So can we think about this from a thermodynamic point of view? And so in other words, what do fully sustainable worlds look like? So this is a paper that we just came out recently, just in the fall. And what we did is we proposed a classification system for planets based on their free energy generation. Basically, the ability to take sunlight, both energy and entropy, and then do things with it, to develop a cascade of power that allowed evolution and interesting things to happen. Now, we did this classification scheme, I'm going to talk about it in more detail, but we didn't do it for detection. The referee was like, oh, this could be very useful, this classification scheme for detection. So it may be, but that's not why we were interested. What we were interested in was the thermodynamic interactions between a coupled planetary system and a sustainable exo-civilization. Could we tell something about what you need to do to reach sustainability? Now, another thing that was interesting was that the referee said, oh, this is like the Kardashev scale. So I'm sure many of you are familiar with the Kardashev scale. 1964, Kardashev proposes that civilizations run through a sequence of evolutionary stages where type 1, you could use all the power that's falling on your planet. Type 2 was all the power coming from your star. And type 3 was all the power using from your galaxy. And here's, if you want, this became a very powerful idea in science fiction. So if you've read the Foundation trilogy, Trantor, the city covered by, the planet covered by a, many miles deep city, was this idea. It's a very, it was an alluring scientific idea for people in the 60s, the gleaming technopia. But the primary lesson of the Anthropocene is, you can't ignore the biosphere. So in some sense, this idea of a type 1 world where you just have, taken all the energy and done whatever you want to the planet is planetary brutalism, and the fundamental lesson, and this is important, that of the lesson of the Anthropocene is you can't bring a planet to heal, right? You have to take into account the dynamics of the biosphere itself, or if you don't take it into account, you do it at your own risk. So you can't bring a planet to heal, but maybe you could bring them a plan. And that's what we were looking for here. What would that plan look like? So what we were interested in was looking at energy, entropy, and power cascades in planetary processes. So one way of thinking of this is that, planets are nature's way of taking sunlight and making something interesting with it, right? Whether there's life on the planet or not, right? You take sunlight, the entropy and energy in sunlight, and then you drive various systems from it. What we were interested in is looking at the cascade of those systems. So, for example, you heat the atmosphere, or you heat the surface, right? And if you have an atmosphere, that leads to convection. The convection will start, moving air around. You'll even get transport of volatiles from that. And so that's the power in. There's going to be a certain amount of power in the climate systems. And because of that power, you're also going to do weathering and other things. And so there's going to be some power in chemical systems as well. You're going to be changing the chemical state of the planet. If there's biology happening, things like photosynthesis, respiration, I put flatulation in here for a reason, and I'll tell you in a second. But there's going to be power cascades through the biosphere. And then, of course, if you have a technology or a civilization, there will also be will be feeding off of that, right? You'll be taking some of the net primary productivity that the biosphere is producing, as well as perhaps just directly from solar via solar cells or whatever, and you're going to be doing interesting things. So we were interested in looking at classifying planets by this, how strong each of these might be. So the flatulation part here is when I worked at Goddard Institute for Space Studies in the 1980s for a year between undergraduate and graduate. And one of the jobs they had me do was go out and find where all the cows in the world were. Because methane, the flatulation turned out to be a very important source of methane. So I kept that with me for the rest of my life. That, biology also includes, flatulation. Okay, so this idea of thinking about power cascades and disequilibria and dissipation, people have already sort of thought about this for biosignatures. So there's this wonderful paper by David Catling and his group on detecting biospheres from thermodynamic equilibrium. And what they looked at was they came up with a measure of Gibbs free energy, and they did this very powerful, very detailed calculation to get a measure of the Gibbs free energy, which was the chemical disequilibrium or dissipation in the atmosphere. And they found that Earth was, quite a bit above all of the other planets in the solar system. So for them, the idea of thinking of dissipation or disequilibrium, which is also transforming free energy, as being a good way of sort of, classifying planets. So we wanted to take it to the next level. So here are 5 classes of planets. First one is you've got a planet that has no atmosphere, Mercury, right? Basically, all you can do, sunlight falls on it, it warms the surface, end of story. If you have volatiles, if you have fluids, now interesting things can happen. You can, you're going to drive convection, you're going to drive evaporation and condensation, and all of these things now are going to be new processes. You've innovated in some sense, and opened up new processes for feeding energy and entropy through the planetary system. So that's a class 2. Class 3 is if you have a little bit of life, right? We call this thin biospheres. Like this is Earth during the Archean. You've got, the life is doing something, but it has not completely changed the planet. Class 4 is what, Earth before us. That was, what we call a thick biosphere, where really, you now have very strong coupling between the biosphere and the other systems. And then for us, class 5 was, okay, now you've got technology drawing power out of the biosphere and out of these other systems, whether it's tides or whatever, to create a sustainable version of itself. So what might that look like? What do you have to do? In some sense, you can think of this almost as an evolution, perhaps in some cases, right? Obviously, if you don't have volatiles, you're never going to get anywhere from beyond a class 1. But if you're a class 2, you could imagine an evolution all the way through a class 5. And if you actually we did this calculation where we looked at the power in geochemical processes, biological processes, and anthropogenic processes, for the different classes of planets. And, when you can ask me how we got these calculations, but we basically used the Earth either now or during the Archean. And what you see is as you go from during a class 2, all there is geochemical processes. Class 3, there's both geochemical and biological. Class 4, you can see that the biological is outweighing the geochemical by quite a bit. Life really dominates the evolution of the planet. And then here is a class 5, a fully sustainable. And what we did here is we calculated desert greening. What if you tried to, allow both, balance the biosphere and draw more power by greening things like the Sahara? So we calculated the amount of power that would, the amount of free energy and dissipation that would create. And it's, turns out to be more than what the biosphere now is doing. So would be a class 5. This is us right now, which we consider to be sort of a hybrid planet, where, we're not quite class 4 and we're not quite class 5. But what it told us is that in some sense, in order to be a sustainable civilization, all boats have to rise. You have to come into some kind of cooperative relationship with the biosphere, where it's like, it's not just you who's producing more power, the civilization, but you got to help the biosphere produce more net primary productivity. And again, this is clearly speculative, but it was a way of, is this a useful way of thinking about what the target looks like? Because really, we don't know what the target looks like when it comes to the Anthropocene. Huge amount of debate of A, is it possible, and B, what does it look like? So, is this what sustainability looks like? A cooperative, all boats rise relationship with the biosphere. So, you have a technological civilization, but it's not Trantor. It's not a world-girdling city. It's a thriving biosphere because those biospheric functions, those services, as sometimes people call, are necessary for the health of your civilization. Okay, so now just a couple more minutes and I'm done. Because, for me, as I said, part of this whole project came out of my interactions with the public. I do a lot of stuff with the public and talking to people about climate change, trying to figure out why, trying to convince them that, like, look, this isn't about politics. This has nothing to do with Donald Trump. This is just science, right? But this perspective, I think, raises a bunch of really interesting philosophical questions, which actually, I think, upend the usual debate. It's provocative, but it takes the usual debate that we have about business or interests versus the environmentalists, and it twists it around in a way that, I think it can really be eventually, I think it's both true, but I also think it can be very helpful in getting out of this thing that we're locked into. So if we think about sustainability, the first question is, what exactly are we trying to sustain, right? And what are the moral imperatives that we're invoking when we try to do that? So what do I mean by this? Right? When we talk about climate change, there's often we're going to invoke pictures of lonely polar bears on ice floes, and it tugs at everybody's heart, which is kind of funny because, polar bears are amazing predators. They'll, rip your head off and drink your blood and be very happy about it. But somehow we get all, sort of soft and cuddly about them. But nobody, so we're like, oh my God, we can't let them go extinct. But nobody's crying about the velociraptors, right? I mean, nobody's like, oh my God, the velociraptors aren't here. That's so terrible. And I bring this point up just to say, like, look, the biosphere, we have to think in terms of the biosphere. And when people say that the problem here is we have to save the Earth, that deeply misunderstands, I think, what planets are. Planets are literally, mechanisms for channeling cosmic scale energy. And so the Earth is going to be just fine. It's not a little bunny rabbit, that we have to pet. It's us that is, we're the ones who are threatened, right? On long enough timescales, the planet will just move on without us. So now I want to be clear. When I say this, sometimes people are like, oh, what you're saying, we shouldn't do anything about climate change? No, climate change poses an imminent and possibly existential threat to the project of civilization. And it's imperative that we initiate coordinated action to deal with it. But the problem that I've certainly seen as I'm, dealing with people is that, you can show people, we've been showing people this plot for 30 years. It hasn't made a dent. We still, the Paris Accords, as everyone knows, are pretty weak. Thank God we have them. But, and the reason that's true is because, narrative is important. People understand themselves and their world through stories, not through graphs. We understand the world through graphs because we're scientists. But most people, this is not how they think about the world. And so the question is, what is the story of climate change? What is the story of human beings and climate change? And what I'm going to argue is the astrobiological perspective gives you the right story, and perhaps a very motivating story, right? So it's about the astrobiology of the Anthropocene is about the right questions and the right story. So the wrong story is what I call the we suck narrative, right? That human beings, and you hear this a lot, we're a plague on the planet, which has to be saved from us, right? But the right story is we're what the biosphere is doing now, right? 100 million years ago, the biosphere was doing dinosaurs, and that was great. It was inventing lots of new dinosaurs. That was affecting the planetary systems. Later on, it was grasslands. That was, awesome. What can you do with grasslands? And right now, it's a technological civilization, right? And each of those changes led to, there were also changes in planetary states. And the thing is, the Earth has done this before. It'll be happy to move on without us. That's the real lesson, right? The Earth will just move on without us. We're an experiment that the biosphere is running, right? And we want to be, the goal is to try and stay part of the biosphere. So that's why this, oftentimes I get into arguments with people, did we change the climate, right? I have to go through all these arguments about, yes, the answer is yes. And I've given up on this question because you just can't dislodge people from this. But I often can change the debate by saying, look, we built a world-girdling civilization. What else did you expect to happen? Right? That's the astrobiological perspective. You can't build a civilization. You can't be this successful as human beings are, and not expect feedback. It's just the rules of planet, right? We've learned to think like a planet from all of our studies of Mars and Venus, etc. And, those rules tell us that if you do what we're doing, here or on other planets, you are going to generate feedback. So, it really can be very useful in changing the debate. So the astrobiological perspective overall tells you that Anthropocenes may not be rare. Triggering an Anthropocene marks a transition for both the planet and the civilization. So this is the most important part for me, the part that really in the narrative that can be inspiring, right? That we are basically cosmic teenagers, right? We are an example of a very immature species, but we have been successful. And there's a certain level at which climate change is like, whoa, human beings have done pretty well. We've changed the entire, chemistry of a planet. But now what do you do, right? As Ray Pierre Humbert, I love this, climate change is humanity's final exam, right? So at some point, you've got to mature. You've got to see the responsibility that you have over yourself, and you have to act on it. So in the end, the astrobiological perspective says, look, it's all about being on the right trajectory, understanding what those trajectories are. We're not the first time it's happened. We're not a one-time story. And can we figure out how to be, winners in this rather than losers? Now you're ending up in the pile, the historical cosmic pile of civilizations that weren't smart enough to deal with the power they had. Okay, so I'll stop there and I'll say thank you very much. And I'll be happy to take questions.
Thanks, Adam, for that different talk. Very unusual, very stimulating, I think, and I expect there'll be a few questions.
Yes.
Happy?
Hi, great talk. Thank you. My question is, you just mentioned that we are an immature species. So what is a mature species? I mean, if we look at the history of the world, small data set, there hasn't been one.
No, there hasn't been one, right? And that's why you do the astrobiological perspective. You want, and that's the whole thing I did about thinking about what does a sustainable biosphere look like? What does a planet with a civilization that has come into sustainability look like? That would be a mature civilization. It would have learned the lessons. It would have learned how to think like a planet enough to be able to, see the route to that kind of planet and take the actions.
Warren?
So what's the distribution of lifetime L that you come up with?
No, so we haven't, all we have right now is those simplified models, which are all non-dimensionalized. So that's the next step. I wouldn't want to give that until I actually put in real physics, like those feedbacks. So, it gives me something to do.
So what about the escape option? One must go elsewhere.
Well, I think...
Can you repeat the question?
Repeat the question.
Can you leave and go somewhere else? So this is interesting. Actually, right now, my student and I are actually working on something. We're trying to work with the Fermi paradox and see how can you get out of the Fermi paradox. And it turns out, I think, certainly that becoming an interplanetary species is, I think, if we make it through climate change, that's what we're necessarily going to be, and that may be part of it. But, good planets may be very hard to find. So having 7 billion people on Mars, we talk about terraforming, but we don't even know if terraforming is possible, right? Maybe you can't, you try to terraform and the climate you develop will just collapse. So I think, being an interplanetary species will be an important part of our maturing, but still your home world, is going to be always going to be an important part because it's hard to get things out of the, the gravity well. So moving your entire population somewhere else, unless you're lucky. One of the interesting things about the M-dwarf planets is that you've got, all these planets that are very close to each other. Like the trip would be a week, with the lunar rockets to go from one planet to the other. So, I don't want to constrain things too much, but I think, it's a lot of it's going to be about dealing with the planet you were born on.
Do you see in these studies any trajectories where things reach sustainability without a decline in the population?
Yeah, no, there are absolutely parameters, where you can get, what we call the soft landing. Where you just, the population rises, it heats up the planet, but then you reach that steady state without sort of having to depart. You don't fly around parameter space as much. You go right up the isocline.
So you have to be thinking ahead.
No, there are solutions that are there. There are solutions that are just, so you don't, even without changing the resources, there are still solutions that are sustainable. So it's a lot, and that depends on, if you look at the parameters, the non-dimensional parameters, you can see that some of these parameters they're a measure of the fragility of the system. If you push it, how quickly does it roll away? Some are measures of the sensitivity. If once your population starts rising, how much does the planet respond? So the question would be which parameter is the Earth like?
Jessica.
So would it be possible for an advanced civilization to try to be invisible as a way of lasting longer? Are there ways that you can be an invisible civilization that can affect your planet, but if you're affecting it in a very stable way, it might not actually be a visible thing?
That's a really interesting question. So, if you think this idea was crazy, Gavin Schmidt and I are about to publish a paper where we were asking whether or not, how would you know whether or not there had been another civilization on Earth 100 million years ago, right? And this paper came out because I went in, I was pitching Gavin this idea, and he out-crazied me in like 5 minutes. I was talking about aliens and climate change. He's like, well, how do you know there wasn't a civilization a long time ago on Earth? And the point is, he was asking the question of, after 100 million years, there's no artifacts left. Everything all soil's turned over, or all ground's turned over. And so the idea when we looked at this was, one thing is, if you become sustainable, you leave less of an impact. So, if you're a dinosaur civilization and you are very sustainable, that's probably going to mean that you're not leaving much of an impact. So in some sense, it may be that sustainability requires some kind of invisibility. in some way, like for technosignatures, but yeah.
I wanted to ask one question. When you were talking about the nonlinear terms, what are some examples of that? I was thinking of the, if we really cut down on CO2, but the Siberian tundra has already melted.
Yes, exactly. Methane, there's a bunch of, people talk about tipping points in Earth system science, that there's all these things that could act as tipping points where, once you've gone past the thing, you can't come back. And so, I think the clathrates, they're called, the methane up under the sea as well. That's an example. Glaciation. I think there's a few, we'd have to go back to the literature, but there's a few things that people really identify as, as tipping points, is once you've gone over, it may be hard to come back.
Phil?
Yeah, Adam, since there seem to be a lot of planets in habitable zones, and there's no evidence of signals or contact from other planets to us, does that put an upper limit on how long a technological civilization would last? I
don't think so. So this is a conversation that Jason Wright and I have had. And this is Jason's point, and I think it's Jill Tarter's brought up, is that when you look at the parameter space that we have actually searched, the number of SETI things that we've done where we've actually gone and looked out, I think it was Jill Tarter's metaphor, that's basically a thimble in the ocean. So the idea that there's this great silence in the sky, I think, is not true. We just haven't really looked. The parameter space is gigantic, and Manazi and Avi have done work on this. So I just think that we just haven't looked in a way that gives us any real constraints about how frequent it happens in the universe. And some people will argue with me with that. David Brin thinks that ours, but
just one or two more, Gary.
I asked this question because a lot of prominent people have raised this as a warning, but people have argued that as biological entities, we're a transitory event on our way to a silicon society. And I'm wondering whether you've given any thought, if that is in fact not an outlandish premise of where these trajectories might go.
Yeah, so that's a really interesting question. And I think, what I'm particularly interested in, I'm actually, I'm interested in the trajectories, for the next 1,000 years or so, because that's, because who knows what comes up after that. So I'm really interested in this project, in trajectories through the Anthropocene. But this ultimate question about whether or not, it's machines that basically, in the end, if you find life in the universe, it's going to be machine life. It's possible. I'm a little suspicious. Because first of all, I think our ideas about consciousness and and the idea, you see this in the singularity that we're going to download ourselves into computers and such doesn't really have much understanding about what consciousness is, and whether or not we're going to create true artificial intelligence. Still, we're developing amazingly powerful things, but it's not anything like our intelligence at all, because the way we're using deep learning and big data and such. So it's entirely possible, and it makes sense to me in a certain way. But I also would put a strong caveat in that, we have these science fiction dreams about what's going to happen to our machines, and yet, I think underlying that is some really deep unknowns.
One might also.
Sorry.
Just a quick question. I didn't hear in your list of limiting episodes, let's call it that, nuclear self-annihilation.
And I don't put that in there. I don't put that in there for a reason. No.
But there's no particular reason to suppose that is still not an issue.
That's true for us, but nuclear, to assume that everybody is going to possibly blow themselves up nuclear is like a giant sociological leap. So what I think is useful about this is that any civilization that is creating a civilization will likely, or that's what we'll see, will trigger climate change. You have to have a certain kind of, your genetic heritage, your evolutionary biological heritage has to have a certain amount or a certain kind of characteristics that you're willing to build the weapons in the first point, right? You can imagine lots of species going like, are you kidding me? We're not going to do that. So, I think you can argue that nuclear warfare would not be universal, depending on, but climate change will be. So that's kind of my response.
One last question.
What do you see as the role of facilities like the Biosphere 2 and Oracle for calibrating the trajectories of your models?
That's a great idea. No, right? I think that's, I hadn't thought about that before. That could be very useful, right? Because that's, Yeah, right now I'm doing it all theoretically. In some sense, almost by treating the civilization as just a biospheric input. You can have biosphere models. People do this, and so we're just using the civilization's in some sense not special in this way. It's just another thing the biosphere is doing. But yeah, to actually do experiments where you could try and I mean, the Biosphere 2 thing is so funny because it started off and it was kind of like totally goofy, right? They all had those 70s science fiction or 80s jumpsuits. But it's turned out to actually, nobody knew that it was going to turn out to actually be some useful science coming out of it. So that's a good point.
Okay, let's thank Adam for interesting.
Thank you very much.
Yeah, I noticed you were.
It's like it feels like it's in flames, but right here.
Did we stop? Oh, sorry.
No, not yet.